All right, got that big distributed systems exam coming up? Don't sweat it, you're in exactly the right spot. We're gonna break down everything, and I mean everything you need to know to absolutely ace it. Let's get right into it.
You ever stop and think about it? How can you search for literally anything at any time or, binge watch an entire series without a single hiccup? It feels like magic, right? Well, spoiler alert, it's not. It's all thanks to something called distributed systems. And today, we're going to peek behind the curtain.
Okay, so here's our roadmap. First, we'll nail down the basic definition. Then, we'll run through the 7 key characteristics, and we're going to spend some extra time on reliability versus availability because examiners love that one. After that, we'll see how you actually build these things to be resilient. And finally, we'll dig into how all the different pieces of the puzzle talk to each other. Sound good? All right, let's start at square one, the fundamentals. So what is a distributed system, really? And more importantly, why do we even bother with them? Because let's be honest, they can be pretty complex. Okay, get your pens ready because this is the textbook definition you'll want to have memorized. A distributed system is a collection of independent computers that appears to its users as a single coherent system. The magic words there are single coherent system. You see, behind the scenes, it could be thousands of computers all over the world. But to you, to the user, it just looks and feels like one solid, seamless thing.
And this visual really gets to the heart of it. On the left, you've got your classic tightly coupled system. All the brains, the CPUs, are sharing one big chunk of memory. It's like a whole team huddled around a single whiteboard. Everyone sees the same thing instantly. But on the right, that's our distributed system. It's loosely coupled. Every computer has its own private memory. It's more like that same team, but now they're all in separate offices. If they want to work together, they can't just look at the whiteboard. They have to actually send messages back and forth.
And just a quick vocab check, because getting the lingo right matters. Those individual computers that make up the system, we don't just call them computers. The proper terms are nodes or sometimes sites. So from now on, we're talking about nodes.
So why go through all that trouble of separating everything? Well, the payoff is absolutely huge. For starters, you can share info and resources way more easily. You get faster response times. You get much higher reliability, and that's a big one, because if one node goes down, the whole system doesn't crash. It also means the system is extensible. You can just add more nodes as you grow. That's how services scale up to handle millions, even billions of users.
Okay, now that we know what they are and why we use them, let's dig into their essential properties. Think of these as the personality traits of any distributed system. We're going to cover 7 of them, but I want you to pay extra close attention when we talk about reliability versus availability. Trust me, it's a classic exam question.
All right, here they are, the big 7. You've got scalability. Can it grow? Reliability, does it give the right answer even when things break? Availability, is it switched on and ready to go? Resilience, how well does it bounce back from problems? Efficiency, that classic trade-off between speed and how much it can handle. Serviceability, how easy is it to fix and upgrade? And finally, openness, does it play nice with other systems? Now, like I said, we're really going to zero in on reliability and availability because that's where the points are. So let's start with reliability. This is super important. Reliability isn't just about the system being on. It's about the system being correct. A reliable system is one that keeps on chugging along, giving you the right results even if a few of its nodes have failed or are acting up.
Now let's contrast that with availability. This one's a bit more straightforward. It's basically just a measure of uptime. What percentage of the time is the system online and ready to do its job? Think of it like a shop's open for business sign. If the sign is on, it's available. If it's off, maybe for maintenance, it's not.
Okay, here is the key takeaway, the point you absolutely have to get. A reliable system is, by definition, available. But, and this is the important part, an available system is not necessarily reliable. Think about a bank's ATM. It's on, the screen is lit up, it's available. But what if it shows you the wrong account balance? Well, it's not very reliable, is it? See the difference? You can have high availability just by fixing things fast. But reliability means it doesn't give you bad data to begin with. Getting this distinction right, that's how you get the top marks.
Okay, so theory is one thing, but how do we actually build these systems so they don't fall over at the first sign of trouble? That's where the concept of resilience comes in.
This is basically the engineer's bag of tricks for building tough systems. Let's run through them. First, replication. Just make lots of copies of your data. If one disappears, no big deal. Redundancy. Have extra hardware just sitting there waiting to jump in. Failover. That's the automatic process of switching to that backup hardware. Checkpointing. It's like hitting the save button in a video game, periodically saving the system state so you can restore it after a crash. Then there are consensus algorithms, fancy things like Paxos that help all the nodes agree on what the truth is. And finally, a classic, load balancing. You just spread out the work so no single node gets buried.
All right, we're on the home stretch, our last big topic. We've got all these independent nodes, right? So how on earth do they coordinate with each other? How do they talk so that they can act like that single coherent system we talked about at the beginning?
And this comes back to that fundamental challenge we brought up earlier. Remember the separate offices? These nodes don't share memory. One node can't just look over and see what another node is thinking. It has no way to just peek into another node's memory.
So what's the solution? Well, it sounds simple, but the details can get tricky. They communicate by passing messages. That's it. Every single thing they do together, sharing data, giving commands, checking status, it all happens by sending a little message across the network.
And one of the most common ways to do this message passing is with something called a remote procedure call, or RPC for short. The best way to think about it is ordering food at a restaurant. You are the client. You tell the waiter your order. Those are the parameters. The waiter takes that order to the kitchen. That's the network transmission. The chef, who is the server, cooks your meal. That's the execution. Then a runner brings the food out, and the waiter serves it to you, and your request is complete. Simple as that. That's RPC.
Now, these messages can be sent in two main styles. First is synchronous. That's where the sender waits for a reply before doing anything else. It's like making a phone call. You're stuck on the line until the other person responds. The other style is asynchronous. That's where the sender just fires off the message and immediately moves on to other things. That's like sending a text message. You send it, and you don't just stare at your phone waiting for the reply. As you can see here, async is way more flexible and allows for more stuff to happen at once, but it's also more complex. Why? Because you need a place to store those messages, a buffer, until the other side is ready to read them.
And speaking of that buffering, there are a few main strategies. You could have a null buffer, which basically means no buffer at all. The sender has to wait. Or a simple message buffer, which can only hold one message at a time. Then there's the dream scenario, an unbounded capacity buffer, which can hold infinite messages. But, that's not really possible in the real world. So in practice, what we see most often is a finite bound buffer, a mailbox that can hold a specific, limited number of messages.
So there you have it. We've covered what distributed systems are, their most important characteristics, and how all the parts talk to each other. You've got a really solid foundation now to go in and crush that exam. But I'll leave you with this one thought. The question that really leads to the next level. We said we use replication to make systems reliable, right? We make copies of the data. Well, if you have multiple copies of the same data all over the place, how in the world do you make sure they all stay the same? How do you keep them all in sync? That, my friends, is the challenge of consistency, and it is right at the heart of the absolute hardest problems in all of distributed systems.